Hi, today I will present our work Flex, full body grasping without full body grasps. Given a 3D scene with objects placed in it, our aim is to generate realistic 3D humans grasping the objects. The grasp should be scene aware, meaning that the human shouldn't intersect with the furniture. This is a challenging task. Capturing humans and objects together is tedious, and methods trained on this data do not generalize to normal configurations. Our key insight is to combine full body pose and hand grasping priors to generate full body grasps. To this end, we contribute the ReplicaGrasp dataset containing everyday objects in a variety of configurations. Quantitative results showcase our method's superiority compared to baselines on existing datasets as well as ours. Qualitatively, we generate diverse, realistic grasps as validated by user studies. We discuss more details next. Data collection for full body grasping is challenging. Existing works place mocap markers on the humans and objects and use a high-resolution multi-camera system to record interactions. Such capture and fitting often requires multiple skilled technicians to ensure clean data. However, it is practically impossible to capture all possible ways of interacting with the ever-changing physical world. The number of scenarios grows exponentially with every considered variable, such as the human pose, object class, or scene characteristics. Methods trained on such data fail to generalize when the object appears in a different position than seen during training. This results in the hand not even touching the object, unrealistic poses, or buried humans. Further, such methods are not able to account for furniture. However, in realistic scenes, we expect to see objects on the top shelf of a cupboard, inside a refrigerator, or the bottom of a shelf. In this work, we aim to answer the fundamental question: do we really need full body grasping data to solve full body grasping? There already exist a lot of efforts in human motion capture and modeling without objects. This covers a variety of poses. Additionally, hand-only grasping is a very well-established field with recent advances already nearing human performance. Given access to these data sources, we seek to learn a prior over each source and combine them to generate full-body grasps. Such a method would neither require full-body grasping data nor suffer from the limitations of such datasets. Towards this, we present Flex, full-body latent exploration. Flex takes as input a 3D object on a furniture item as shown. Given access to a pre-trained hand-grasping model, we search in its latent space to find the wrist angle alpha and latent code W that produces mano-hand parameters, resulting in a feasible hand grasp as shown in green. Next, given access to a pre-trained full-body pose prior, we search in its latent space to find the latent code B that generates a body pose. Finally, we also search for the full-body translation and orientation that, when passed to SimpleX, generate a 3D human as shown in blue. Additionally, we learn a data-driven pose ground prior, which predicts the floor given the body pose. This serves as an additional constraint. We delegate the burden of controlling the multiple optimization parameters to a single controllable latent vector Z. Specifically, we learn a mapping MLP from the latent vector Z to the different parameters and train them to minimize the loss terms, resulting in the best full body grasp. We will now describe each component individually, starting with the hand matching loss. Our key insight is that we can combine the hand and body meshes because there exists an anatomical connection between them. The hands have to match. Thus, given the body and hand vertices, we align them by minimizing the L2 distance. Next, we discuss the gaze and obstacle avoidance losses. The gaze loss encourages the human to look at the object. We use the head direction vector, which goes from the back to the front of the head. Then we compute the vector from the back of the head to the target object. The gaze loss minimizes the angle between these two vectors. We introduce a novel obstacle avoidance loss that penalizes body obstacle penetration. Traditional losses penalize only the portion inside the obstacle as shown in yellow. Besides this, we highlight the importance of penalizing the region of the human arm inside the obstacle, shown in pink. We address this by treating the human mesh as a graph. When part of the body penetrates an obstacle, two or more components of this graph get separated, resulting in a disconnected graph. We then penalize all vertices that are not part of the largest connected component. Here, the pink and yellow parts are penalized. Finally, we discuss the last component of flex, the pose ground prior. Simply enforcing the losses described so far can result in a flying loop. To make the human pose reasonable, we learn a prior over the relationship between human pose and ground location. Given the human pose, the pose ground prior predicts the pitch, roll, and vertical displacement of the human that identify where the floor should be. We can thus visualize the floor and optimize the global parameters so that the floors line up. The pose ground prior is trained on 12.7 million examples of AMA's dataset using a 2-layer MLP. This is kept frozen during inference. This completes our discussion of the approach. We can now see all these components in action. As the optimization progresses, we can see both the human and the grasp mutually evolve so as to match each other while avoiding penetration with the cupboard. We contribute a challenging and representative benchmark to study this problem for full body grasping, called ReplicaGrasp. ReplicaGrasp consists of 50 everyday objects from the graph dataset based on 48 receptacles from ReplicaCAD, simulated using the Habitat Simulator. In total, we contribute 4.8K instances. We show some qualitative comparisons on ReplicaGrasp. Notice how the baselines are unable to account for the obstacles. Further, the poses are often unnatural, especially at taller or shorter heights. In contrast, Flex generates much more plausible poses that can avoid obstacles. Flex also has the added advantage of generating a diversity of full body grasps depending on the initialization conditions. The grasps shown here are the top 5, resulting in the lowest loss values. The diverse poses indicate that the optimization manifold is well learned. We quantitatively evaluate our full body grasps against both baselines. We find that Flex largely outperforms both the baselines on the graph dataset. Note that the baselines have been trained on graph, while Flex has never seen this data. This indicates that full body grasps may not be necessary to solve this task. Additionally, we also perform both baselines on ReplicaGrasp. We summarize our contributions as follows. We presented Flex, a framework to generate full body grasps. We contribute a benchmark called ReplicaGrasp and demonstrate that Flex can produce full body grasps that outperform baselines. Our code, data, and pre-trained models are available on our website. Thank you.